Hello everyone, let's solve this problem. Is the given statement correct? A ketone can be prepared by the reaction between a nitrile and the Grignard reagent. It begins with the formation of an imine as an intermediate and then the hydrolysis of the imine to a ketone. So before we go through the steps, let's first label the different components that the question is asking us about to see if we can start confirming if this statement is A, correct, or B, incorrect. So the question states that we start with a nitrile, which we actually do have here, and a Grignard reagent, which we also have. So far, so good. That allows us to have the formation of an imine intermediate. So where are our imine intermediates? Well, they are here and here because they both involve the carbon being double bonded to the nitrogen. Finally, we have the hydrolysis of the imine to a ketone, which we do have. So now let's go through the 3 steps. Step 1 of the mechanism is when the organometallic reagent's nucleophilic carbon reacts with the polar nitrile group's electrophilic carbon, and the electrons from the nitrile move to the electronegative nitrogen, forming this imine salt complex with the negatively charged nitrogen. Step 2 is the protonation of this negatively charged nitrogen of the imine salt complex intermediate by hydrochloric acid. And step 3 involves the acid catalyzed hydrolysis of the imine salt, which involves the formation of a tetrahedral compound and collapse of the tetrahedral compound. So when we have the formation of the tetrahedral compound, where there's the carbon single bonded to 4 different things, it's going to be a little bit more involved. So let's go through those steps together. So these are the steps involved in step 3, hydrolysis, to give us our final ketone product. So we start with this imine salt complex intermediates, which has nitrogen double bonded to carbon. And we have hydrochloric acid and water. Hydrochloric acid in the presence of water. Whenever we have an acid in the presence of water, we are going to form something in solution called hydronium ion. I'm sure you are very familiar with this. It has a structure of oxygen bonded to 3 different protons with a positive charge. It's very acidic, and in this case, it can be useful because this nitrogen has one lone pair of electrons, which allows it to be protonated and give us our next intermediates with the positively charged nitrogen atom. Perfect. So now we need to form our tetrahedral intermediate. In order to do so, we need something that can act as a base to attack on this carbon to open up the double bond. So what do we have in our solution that can act as a base? Water. Exactly. We know that water can act as an acid or a base depending on the situation due to the 2 pairs of lone electrons. So that's exactly what's going to happen here. This oxygen is going to attack on this carbon, resulting in the electrons of the double bond moving to nitrogen and neutralizing it, giving us our next intermediates with a neutral nitrogen, no double bond here, and the addition of our water group. Keep in mind, the oxygen does bring over its 2 protons, so it is still positively charged. So our next step is to neutralize this positive charge. So we need something to act as a base again to deprotonate, which again will be water. And it will deprotonate one of these protons, leaving these electrons for oxygen to neutralize it. And we will get our next intermediate. That will look like this. Perfect. So now we need something to act as a leaving group so that a double bond can form between this carbon and the oxygen, and we can have the collapse of our tetrahedral intermediate. So we can see here and here that we have achieved the tetrahedral intermediate with carbon being bonded to 4 different things. So out of the 3 groups, NH2 and our 2 alkyl groups, which one is a good leaving group? Well, it's kind of a trick question because right now we don't really have a good leaving group. We need to make something into a good leaving group. What we will make into a good leaving group is the NH2, because we know if we protonated one more time, it will be NH3, which can then leave, right? So what can we do to protonate this NH2? Well, we still have hydronium ion in solution. So that's what we can use to protonate one more time. Okay. So when nitrogen takes that proton, it will now become NH3, which is a good leaving group. And now we need to form the double bond between oxygen and carbon. In order to do that, electron rearrangement will occur with one pair of lone electrons forming this double bond, allowing this is positively charged, very important, allowing this NH3 to leave. Perfect. So once that happens, we will get a carbon double bonded to oxygen that is still bonded to the hydrogen, so it's positively charged. And we still have our 2 side groups. And now we have NH3 kind of chilling around in the solution, right? Perfect. So now we need to find a way to get this proton off so that we can have a nice neutral carbonyl ketone. So this is actually a base that can do that. So that's exactly what's going to happen. This lone pair of electrons is here, which is going to allow it to deprotonate. And now we're going to get our ketone, final product, and we're also going to have NH4 plus. And remember, up here, we did have hydrochloric acid, where this proton left to go to water to become this hydronium ion. So we do have in solution our chlorine ion. So keep that in mind. The chlorine and the quaternary ammonia are going to make an ionic bond, and you can write that as NH4Cl. So our final answer is this ketone and NH4Cl. Thank you very much for your time and attention. We can confirm that the answer to this problem is A. The given statement is correct because we end up with the same ketone final product through the steps outlined in the question. Have a great day.